Okay, so today we're going to talk about power. This is probably conceptually the most difficult lecture to understand. It's not long, but it's complicated. Ask questions and pay attention. Okay? So we care a lot about type 1 error, in fact, so much so that we set the alpha level, right? Probably of a false positive. We set the value. We 0.05 or whatever. Our software, in fact, gives us exact p-values. If you've played around with SPSS, and I encourage you to have done that at this point, but any other statistical software does this too, it actually gives you the exact p-value when it does a calculation. Okay? So it's telling us this. I guess the first question one might ask oneself is, well, or not the first question. First would be maybe why do we exist, something like that. But when you start thinking about this stuff statistically, you might say to yourself, why do we care so much about type 1 error and not about type 2 error? That's a false rejection of type 2 error. We care about false positives. Why don't we care so much about false negatives? Because it looks like we care more about false positives than false negatives. Well, historically, part of this is the way this was set up in the first place. When Fisher first started doing the real logic of hypothesis testing and working on the F distribution, he actually thought of the null hypothesis being a real thing, not a straw man. What we basically do with hypothesis testing is we set up a straw man, right? It's something we want to destroy. Right? You know, like when you argue with somebody and you set up a straw man argument so you can destroy that argument. Fisher didn't think of it as a straw man. He thought of the null hypothesis as a real thing. So I think part of it is that. And that's sort of philosophical. All our methods are set up this way, and in fact, it's probably the only way they can be set up. We have to assume there's no effect. Because would we start assuming there is an effect and say it's this big? That would be hard, right? Because the question you would ask immediately is, well, how big is the effect and why is it that big? It's much easier to contemplate there's nothing happening than, because as soon as you contemplate there's something happening, I'm going to ask you, what is it? And then I'm going to say, how big is it? Right? So it's Bob Dylan, right? You know that something's happening, but you don't know what it is. So I did that as an homage to an old stats prof. As he said in class once, and no one got the reference but me and two other people. And clearly none of you have listened to Bob Dylan because you're young. Your parents would get that reference. But the point is, if you said you know there's an effect, I'm going to say, how much? Which way? Right? You can't set that up as your beginning point. Does that make sense? It'd be hard to fathom how you would do that, though that's what we're going to do today. So it's easy to set up a situation and to imagine a situation, null hypothesis, where nothing happened. Because as soon as you tell me something happened, I'm going to say, what is it? Where is it? How big is it? What's it weigh? I don't know, let's do that one. What's it weigh? I don't know why that would matter. How could effects have weight? Like I said, for HA, we have to know how big the effect is, not just that there is an effect and what direction it's in. We have to know the size of the thing. So I've now said this like 11 times. Does it make sense? Like, how are you going to do that? Wouldn't be easy. Would not be easy. Okay. In the best of all possible worlds, which we clearly do not live in, we would minimize alpha and beta. That's the probability of a type 1 and a type 2 error. And have the most power, because if we've minimized beta, we're maximizing 1 minus beta. And we want power. Well, if something's there, we want to be able to see it. That's a blind joke, and it's a little offensive. But we want to be able to see it. We want to see this effect. Is it there? If it's there, I want to be able to notice it. Perhaps hear it, or just sense it. I don't know. Instead of seeing it. So we'd have the most power possible and we wouldn't make mistakes. Small alpha, small beta, big 1 minus beta. Wouldn't that be great? Power is the probability of rejecting HO given HA is true. Now there's a problem here, and I told you this a couple of times, that there is a reality, but we don't know what it is. We can't know it. If we knew it, we wouldn't have to do this experiment. So in other words, if we knew HA was true, why would we do the experiment? So to determine this probability, we're going to have to figure out, we're going to have to say HO given HA is true. In other words, we have to know the null hypothesis is false, the alternative hypothesis is true. Now we're going to have to know how big the alternative hypothesis effect is. So all that stuff I just said would be impossible to do. Now we're going to have to try to do it. Oh, grand. This ought to be fun. I don't know what that accent is I just did there. Sort of a mid-Atlantic kind of thing, sort of an FDR kind of approach. So, some of these jokes apparently are just for me. Some of them, many of you probably wouldn't call jokes. I don't care. So, are you with me so far? Questions? That noise was from somebody with construction that wasn't in the room. Okay. By the way, wasn't it great writing the quiz to the sound of a reciprocating saw? That was nice, wasn't it? By the way, the manliest of all possible saws is the reciprocating saw. It's also frightening as hell. You know, you can cut through concrete with it. A buddy of mine, who I taught this class to years ago, is a contractor now. He cut down trees for us once. He does a lot of stuff. We usually pay him. For him, he's like, no, this is fun. He's like 50 feet up that tree, cutting down branches with a reciprocating saw. He's holding extended. He's yelling at Dave, get your phone. Why? So he said, because if I fall, I'll make a great video. So that's, he got it in this class. Strange thing. Okay. This is from the book. Here's the HO distribution. Nothing happened. This is that we have two things that are the same. And we actually make guesses about that. Right? So here's HO. And then we've got, what's that? U sub 0 is going to be the HO. Right? Now, the probability, we're going to say we have an effect if we get a score in this region here. Right? We're going to say we have an effect. And if HO is true, in fact, we don't have an effect. We just made a type 1 error. Right? Remember drawing those pictures in 2126, right? So you just draw it. So if it's passed here, we reject it, even though it wouldn't be true. It's made a mistake. Well, we have the probability of making a mistake. Great, it's 0.05 or whatever the hell we said alpha as. Okay. Now here's the hard part. Let's pretend we know the size of the H1, the alternative hypothesis. Let's pretend we know the distribution for it. We can't know that. Let's pretend we do. If we get a value here along the x-axis or greater, we're going to reject HO. But HA is now true. That's going to be our power. That's the probability of rejecting a false null hypothesis. Here's the probability of us making an incorrect of not rejecting HO given HA is actually true. That's beta. That's here. See how big this amount is? The area under the curve, the probability is pretty high compared to alpha. Questions? Yes, Madison.
So that larger area is the probability of us rejecting HO, or not rejecting HO, but if HO is true?
But HA is true.
HA is true.
Or H1, whatever you call it. This is from the book, they call it H1 in the books. But yes, it's exactly what that is. That's exactly what that is.
Can you say that one more time?
That's exactly what that is. Oh, not that part? I never tire of that joke. Okay. Remember what beta is. Beta is the probability of failing to reject HO given HA, or in this case we'll call it H1, is true. When do we fail to reject? When we get a value here or less. Right? Make sense so far? Mm-hmm. You good? Given H1 or HA is true, that's this distribution. So it's going to be all this area under the curve here from the critical value we've set to the left ad infinitum. Did that help?
Yeah.
Good. Good. Madison.
So power itself is that second curve of AJ, or is it just from the? Okay.
Because power is the probability of rejecting a false null hypothesis. If it's a false null, that means H1 is true. And the probability of rejecting it is going to be anything past the score that we have as the critical value. Other questions? Good so far? If you can imagine this, you're in good shape. You get your head around this diagram, you're in pretty good shape. Okay. Let's move that over here. How would we increase the power? Now, considering we're already doing something insane, which is imagining that there's an effect and how big it is, we can do anything. We can do whatever we want. We're magical beings. We know things that nothing else knows. Well, there's a few things we could do. We could make alpha bigger. If I took this value for alpha and pulled it over, let's be ridiculous. Let's make alpha 0.5, not 0.05, 0.5. Put it here, right at mu1. I get lots of power. I guess I could do that. But I can't do that. No one's going to allow me to do that, right? We talked the other day, we talked about hypothesis testing. No one really is going to let you move your alpha too far with an idea. What if we increase mu1 minus mu0? I said we're magic, we can do that. Let's take this H1 distribution here. Let's put it over here. They don't overlap at all. We have all kinds of power now. The whole thing. We make no beta, no type 2 errors. We'll put it over here. We'll put it like a couple of meters away on the blackboard, no longer on the screen. Is that something we can practically do? Well, no, we can't. Right? We can't. It's hard to change alpha. It's impossible. It's literally impossible to move. What we could do it. We can't practice. It's impossible to do. But we can imagine it. Let's pretend. So there's two things we can't do. We can decrease sigma. What if we just leave the means where they are, but tightened up both those distributions so they don't overlap anymore? What if we tighten these two guys up so much that it's like this, we get hardly any overlap? Well, that'd be another approach. Right? So you see the three ways we can increase the power? The first two are literally, the first one is impractical, because everybody's going to say you can't do that. The second one is literally impossible. And you might say, well, the third one's impossible too, Ned. If we can't move means, how can we move standard deviations? But if we could, that would be grand. We actually can't change the parameters. We can't, because they're parameters. So what are we going to do? Well, we could quit, but that would be pointless. We're not quitters. Retreat? Hell, we just got here. It's a quote from World War I. You really are into World War I history. Okay, good. Battlefield 1, we're just playing that game. Achievement unlocked. You've got dysentery. That'd be a great achievement, by the way. You just sit there and puke your guts out. Our best bet, in fact, is variance. It's the one, or standard deviation, I think in variance typically. If we make the variance smaller, we tighten up the distributions. But we can't make variance smaller. But remember, we aren't actually dealing with population distributions when we make statistical decisions. We're dealing with sampling distribution of the mean, aren't we? We're dealing with the sampling distribution of the mean, not with the population distribution of the scores. We make an inference about the population distribution of the scores, but we'll use the sampling distribution of the mean. Yes? Talked about that last time. Sigma squared sub x bar, the variance of the sampling distribution of the mean, is a function of n. Right? Because the variance of x bar equals sigma squared over n. We can't change sigma squared. Oh, we can change n. Let's increase n. Sigma squared stays the same. N gets bigger. What happens to variance of x bar? It gets smaller. Meaning there's less overlap. Oh, nice technicality. You just want we can affect the power of the test. Doing something that it didn't look like at first we could do. But now we can do it. And we don't have to be magic. Make sense? That's pretty cool. That's a thing. That's actually something practical. We can do this. Now think about this just completely intuitively. What if we somehow, magically, were able to test everyone in the population? Then we'd find a difference if it was there, wouldn't we? Because we've tested everyone in the population. So if n gets infinitely large, we're going to find the difference. We have to if one's there. Okay? Okay? You look like you're a little confused there. Okay? You get it? Good. You know, look at your face like you're quite sure you got it. No? Good. Okay. I don't see that well, so you're wrong. Okay. So, what we want to do is figure out how big an effect we're interested in. Because think of this. You know what? When you compare two groups on something, they're almost always going to be different if you have enough subjects. People aren't exactly the same. Or rats aren't exactly the same, or whatever. So, when we take a look at mu1 minus mu0, or if you prefer mu a minus mu0, that's the size of the effect in the population, okay? So that's the size of the effect, any effect that exists. What we have to do is standardize this to be able to somehow come up with a number to represent effect size. Why don't we just divide it by the standard deviation? Notice how they're all parameters. We actually can't know these things. But mathematically we can represent them. So it's mu1 minus mu0, the whole quantity divided by sigma. So, because we have to take into account the overlap. So that's the variance, or the standard deviation in this case. So we're going to say mu1 minus mu0 over sigma. How do we know how big mu1 minus mu0 should be? Or how big we expect it to be? Well, one of the things we can do is look at prior research. So you go into the literature and you say, how big an effect do people typically find? Okay. So when I say we got two groups and one group scores 1.6, one group scores 1.3 in one experiment. And then you look at another, and you take a look at the variance. And then you look at another experiment. Keep doing this and you say, okay, if there's an effect here in this kind of research, the effect size will be X, Y, or Z. That's one way to do it. And in fact, if you do your honors thesis with me, for example, one of the first things I'm going to ask you is when you come up with your design. And what your question is, I'm going to say, or actually, you'll probably ask me, how many subjects do you think I need? You'll probably say participants, because you've been trained that way. Subject is a bad word. But I was told once in a paper to change subjects to participants, and I said they're pigeons. They didn't sign any consent form. I don't think they're offended by being called subject. So they're going to make it animals. I just wasn't going to call them participants. Anyway!
You have rights to do.
Yeah, sure they do. Rights to be in my experiments. So, I'll probably say to you, how big are the, when they find effects in these experiments, how many subjects they use? Because everybody goes, I want to test 100 people in both groups. Like, yeah, you'll probably find something. Will it mean anything? Who cares? How about 50? Look, all these experiments we've been reading about, they got like 12 people per group. Let's go with 12. They find things at 12. Let's stick with 12. That's a nice rule of thumb to use, right? Not 12. The rule of thumb is if everybody else does it this way and finds something, I'll do the same kind of research. I'll do it that way too, with that many participants. And if I don't find something, it's probably not there. And if I do find something, that should be the right number of subjects. So that's one way to do it. The question you're asking is, how big is a big enough effect that we find it useful? Like I said, if you test enough people, you will find a difference between two groups. It doesn't matter. You will find something. If we took all the psych students and all the computer science students, there's about an equal number of this universe, and we measured the size of their middle toe on their right foot, I guarantee you we find a difference. Who cares? Does it mean anything? Probably not. It's probably some artifact of something. The shoes those people wear are too tight. I don't know. Would that be interesting if we tested there's about 120 psych majors and probably 150 computer science majors? If we tested 100 of each and you found that, would you go, oh, I better publish this because people that do computers have short toes? No, you'd go, so? Now, if you found it with 10 people from each, you'd go, something weird's going on here. So the question is, how big is big enough? Well, there's a way to determine this, and this is what's called Cohens method. It's a rule. This is also just a rule of thumb. But the notion is, if D, that's the effect size, is 0.2, the percentage of overlap in the two distributions is 85%. That's quite a bit of overlap. If it's, and that's called a, quote, small effect. A medium effect, 0.5, that's mu1 minus mu0 over sigma. If it equals 0.5, we still have 2/3 overlap in the two distributions. That's called a medium effect. A, quote, large effect, 0.8, still over 50% overlap in the two curves. So even something a lot of people call a large effect, there's that much overlap. All right. So now what do we do with this information to determine, because what are we trying to do? We're trying to say how many subjects do we need in an experiment given a certain effect size. We're trying to be practical. We combine this information with the effect of the sample size. We use something exciting called the delta statistic. That's not a halfway done 8, it's a delta. Okay. This is for a t-test. There's a version of this you can do for analysis of variance. Delta is a function. Oh, sorry, delta equals D times the effect of n on the statistic you're interested in. In our case, how does n, we're thinking about this in terms of t-test because it's the easiest thing to do. Okay? How does n affect a t-test? Just think about the formula. Well, it's the square root of n, right? That's all it is. Right, because think about the bottom of a t-test that's got the square root of n on it. When I did this, I didn't quite yet know how to do a square root, so it's a check mark. It should be a square root sign. I eventually figured out how to use some equation editing software, which I hate. So f of n is how n affects a given test. So for a t-test, f of n equals the square root of n. Okay? And again, just think about the bottom of the t-test. You have square root of n on it. Right? It uses standard deviations. It's square root of n. That's going to tell us now how many subjects we need eventually in this roundabout way. It's going to tell us. Okay, does that make sense? So we're going to take d and multiply times the square root of n, and that's going to give us some value for delta. Okay. This is actually not that bad. If you know d, which you don't, you can't. 10. And it's, you think to yourself, how big is big enough? And you know what people typically do? Medium. And they use 0.5. One of the things always to remember is if there is a, quote, medium-sized effect, that means that there's 67% overlap between the two distributions. A lot of times in, especially the sort of social sciencey kind of things in psychology, not just those, we find effects and we get all excited, but when you look at how big the effect size is, it's so freaking small as to be not that interesting. Okay? So if you take a look at the difference between men and women in spatial ability on average, which is there, the overlap is like 67%. And same way for the verbal superior for women. Okay. So let's say we know that d is 0.5. In other words, we're going to say it's 0.5 because we're going to say that's big enough for us. And you usually pick 0.5 because it's in the middle. Most people go 0.5. I like 0.5. And let's say we want a power of 0.8. In other words, if something's there, if there's an effect size of 0.5, we want an 80% chance of finding it. That seems a reasonable trade-off. So 8 times out of 10, 4 times out of 5, 16 times out of 20, 80 times out of 100. I can keep doing this all day long. You will find an effect of 0.5 if it's there. That's what we're going to say we're interested in. And again, 0.8 would be a reasonable power to shoot for. Because if I miss it, somebody else will find it. Okay. There's an appendix in your book called Power. Called Appendix Power. Appendix Power. Okay? So this is just looking stuff up on another table. That's all this is. So we're set d at 0.5, 1 minus beta at 0.8, alpha at 0.05. And it's not very easy to see. What this table allows us to do, we have the alpha for a two-tailed test. I think I can zoom in on this. There. So an alpha for a two-tailed test. Okay. And then we look up the power we want. Oh, 0.8, it's right here. And then we go across here. It says 2.89, if I'm reading that properly. Oh, yeah. 2.80. 0.8. 2.8. we actually pull the delta out of a table. Okay? Just pull it right out of this table. So that's not really that hard to do. What have you done? How did you get n equals delta over d squared? I squared both sides and I cross multiplied. It's not magic. Just remember that delta equals, right, f at n times d. So delta equals square root of n times d. I don't want to find the square root of how many subjects I need. I want to find the number of subjects I need, right? So let's square it. So now we've got delta squared equals n times d squared. Do you want to isolate n, right? So you get, whoops, let me scrub my buttons. Delta over n squared equals, delta over d squared equals n. I just skipped a bunch of arithmetic or algebra that you all learned how to do a long time ago before I did the slide. But I thought I'll put it up on the board. I'm not magic. It's not a new formula. I just do make it math easier. N equals 2.8 over 0.5 squared. We need 31.36 subjects to find, if we have a d of 0.5, and we want alpha, and we have an alpha of 0.05, and we have d of 0.5, alpha of 0.05, and we have a power of 0.8. So 32 people. So 32 people. We need 32 people. That's all you do. It's really that simple. Yes, please, Nancy.
So you got that 2.8 by looking up,
Just look up the table, yeah.
and then you put it into.
Just threw it into this. Yeah, that's all you do. I mean, it looks complicated because there's a funny looking Greek letter in it, but it really isn't complicated. It's taking the d that you know, well, no, let me say 0.5, the delta that you pulled out of a table, which said, and to get that value from the table, I need to know the power that I'm interested in, 0.8, and you know the alpha, 0.05. And I go, right there. That's all you do. Let's increase the power. I want more power. So let's increase the power. Let's make it 0.99. If it's there, I wish you found it. The delta value now goes up, if you pull this from the table, to 4.2. 420. So you pull it out, you get 420, you get high, and then July 1st is going to be, Canada Day is going to be fascinating this year. Hey, this is legal. Suddenly I need 71 people. And I think, yes, this is assuming I pulled the right delta from the table, but 4.2 over 0.5. That's more. I've gone up by how much? About 20%, right? Because 19 over 0.99 minus 0.8, so it's 0.19 over 0.8. So I've gone up about, what, so 25% in power, and I've had to double my number of subjects. The question one asks oneself at this point is, was it worth doing this? The answer almost always is not really. And you guys, a lot of you guys are planning, how many of your people here actually are planning to do the honors thesis at some point? Yes, a lot of you, right? Yeah. You'll find that testing twice as many people is probably not a good idea when it's not getting you really a whole lot more. Right? And you'll find your advisor will say, why do you want to test this many people? Power, you'll say. And then hopefully your advisor will say, how much extra power do you get for doing that? And then you mumble to yourself, about 20%. It's not helping much more. You might ask yourself, what the hell is delta? You might ask yourself, how did I get here? Talking heads? Anyone? No? Okay. It's got a name. It's called the noncentrality parameter. We actually typically assume HO. Right? All our statistical tests assume HO. And then we find out how likely HO is. If HO is not true, hey, it's not true, it must be HA. Well, under HO, the expected value of t is 0. Right? Think about this. The expected value of t should equal 0 because, let's expand this. Oh, x bar. What should x, if there's no effect, if HO is true, what should x bar minus mu be? Right? If we did it a zillion times, that's what the expected value says, we do something over and over again, the expected value is 0. What delta is it's actually doing exactly the same thing, but it's saying, assuming it's this big. So it's what's called a non-central t distribution. And it's a parameter because it's something we can't know. Right? We're making guesses, and we're saying how big is big enough. Notice all the huge assumptions we make when we make these power calculations. We try to make them reasonable assumptions, but they still are guesses we're making. How likely do we find a value of delta that is greater than the t value of 0.05, basically, the critical t value? So that's it there. So delta is just x bar minus mu over s divided by square root of n. So that should be an s in the sigma, sorry. On the board, that should be sigma. And it's non-zero. So if you're ever interested, that's what it is. But it's basically the idea of what's the value of t given a certain power, given a certain effect size. It's just basically used to allow us to do power calculations for a t-test. Questions? This is a weird way to think because you have to actually imagine how big an effect is, and you know you actually can't do that. You have to make guesses about how something is big enough. That's not an easy thing to do. It's a weird set of assumptions you make. So I know it's confusing. That's why I said this one conceptually is probably the hardest one of the whole term to get through your heads and understand it. It really is. In all honesty, once we get past the first test, everything becomes exactly the same. It's just it's a variation on a theme until the end of March, which is just analysis of variance, analysis of variance, analysis of variance. You can do this for ANOVA, by the way. What would you say the F at N would be for ANOVA instead of, I know we haven't talked about ANOVA, but you know a little bit. What's the F at N going to be for ANOVA? Because it's not root N anymore. It's dealing with variances, so what's it going to be? Just N. Remember, think about this. S squared, so S squared, you don't have this on a square root quantity, you just got N on it. Or N. So it's going to be just N. There are very simple ways to do this. An advanced statistical textbook, like a graduate level stats book, will have these graphs in the back of the book, and it'll say how many groups, how many independent variables, and then you read a thing from the graph. This is how many subjects you need. Okay? But it's nice to be able to do these kind of calculations. They're quick and dirty, and you're making tons of guesses, right? But the important thing is to do these calculations before you do an experiment. It makes you do a couple things. It makes you think how big is big enough, right? How big enough to care? That's an important question. And Makes you go back and look at some past research. And it makes you think about your experimental design. So this is something you actually should do. And it's not hard to do. It's not. If you work with me or Paul, we can help you do that. You work with somebody else, they'll come to me or Paul and say, how do you do this? And then we'll show you how to do it. So we do. Everyone has different expertise, and we make fun of them. So make fun of Paul, and then Dwayne. To a lesser extent, Lauren and Cheryl, because they have this. Joe, nobody scares me. I fear no one. Questions? So let this kind of sink in. I know it's difficult conceptually, but arithmetically it's actually pretty trivial, right?